proceed here. Yep.
Okay, so if we had number 11, it's pretty much the same as the other stuff, and it actually the linear map from B to W.
Mm-hmm.
Then there's this T, which is a linear map. So B to W subject to be equal to X equal U and U.
Do you want a hint about how to do it? You can write down a specific map that does it.
I think that if I wrote, part of mine said define T from B to W by T of an like A1 U1 plus AN US plus
Sure.
U1, like I could take that in the basis
Okay.
for S, and then I said it was equal to S of A1 U1 plus and then AN UN.
But it doesn't know what to do with those vectors, the extra vectors in your basis, right? That's the problem. If you try to feed it that extended basis, it doesn't know what to do. You have to tell me what it does to those basis vectors. So I'm going to give you a slightly different take on how to do that. Your idea is right, but there's a better way to do it. There's a problem that you're going to run into. So this is what is suggested. That you have U, which is contained in V as a subspace. And you have a map T that takes the subspace into some other vector space. That's kind of the setup for the question, right? The idea is, can you figure out a way to so that you can use a function, you can use T to build a function that can take an input from anything in the vector space and not just in U. That's really what the core of the question is. So one approach would be to say, well, if you have a basis for U, then you can extend that some extra vectors to be a basis for V. Now the problem is if you apply T to these vectors, it doesn't know what to do with them, right? You have to tell me what it's supposed to do. T has no idea what to do to things over here, right? That's the problem. Is it's over here, it's like, oh, I'm perfectly happy. You tell me some linear combination of these guys, I know what to do with it. I'm a linear map on those. What's an idea about what T could do to the rest of this basis? Yeah. Set it to 0. In fact, a more natural way of thinking about what you're doing here would be to say, you guys remember the theorem that says that if you have a subspace, you can find another subspace that is a direct sum to the whole vector space? That if you have U as a subspace, we had a theorem that says that you can find there exists a W so that U plus W is equal to V. So if you ever have a subspace, you can find another subspace that's a direct sum with the original one. And so just define the operator, define the map. Well, T knows what to do on these vectors. So just send everything over here to nothing. That works. I mean, it's not very interesting now, but you can certainly extend T to the rest of the vector space just by throwing things away. Like, oh, so you've got some vectors that, some part of U is in W, just throw it away. Why does this work? So you set T so that T of U is equal to 0 or not 0, T of U is just equal to T of U if U is in U, because that's what T does. T knows what to do with vectors in U. And T of V is equal to 0 if V is in V. So on, no, not V, W, sorry. U is the subspace, V is the vector space, W is the output. So if you were in U, T knows what to do with U. If you were not in U, let's just suppose that part of U is in W, or that you're in W, make T turn those into nothing. Then what does T do to anything that looks like this? T's linear, right? T's a linear map. What should it do to this? C1 TU plus C2 TB. What is all that equal to? This is a perfectly defined map. The reason that we can do this with the direct sum is because every vector in V can be written uniquely as a U plus a W. Since it's a direct sum, anything in the vector space V is written as something in U plus something is W. So just set up your function so that if it sees something in U, it keeps it. And if it sees something in W, it turns it to 0. And that's how this extension works. I meant W here. If V is in, sorry, Oh man, I got W's and U's running all over the place. I meant here. Use the I need another space name.
X.
Okay, X. Yeah, we'll call this. Let's call this W, and we'll call this X. X is just supposed to be whatever the original output space was. Okay. So this is, if you want a concrete example of what's going on here, it's like saying, suppose you have a map that's defined on a line in R2. How can you define it for anything that's off the line? Well, just define it to be 0 on anything perpendicular to that line. Anyway, this is a lot of these exercises, it's actually easy for me to tell you how to do it, but then there's a lot of work in you figuring out why this works. So my suggestion is if you don't see why this example works, you should go look at it. Right? But this direct sum idea or extending the basis are basically the same idea. When you extend the basis, this is like the span of these guys, and the span of these guys are like the set W. So basis can always be divided up like this into a direct sum. Okay, anything else? Yep.
I have a question on 11.3b.
Okay.
I just don't understand the questions, like what's given.
Suppose that you have a pile of linear maps. And they're all injective so that you can chain them all up together. That's really what it's saying, right? So it's not necessarily the case that if I have a bunch of maps that I can compose them with each other. That's not always possible. If I have a map and I have another map, I can't always compose things because the domain and the range might not act correctly, right? So the whole setup of the question is saying the following. Like if you just had two maps and I say, when can I do S composed with T? Well, that only makes sense if the range of T is contained in the domain of S, right? If that's not true, then this doesn't make any sense at all. T has to spit out things that S can see as inputs. So the whole setup of the question is just telling you, look, you have a bunch of maps, S1 to Sn. Suppose they're set up in such a way that this makes sense. So he's not going to say some crazy thing about ranges and domains. He's just saying, I can compose them this way. Whatever it is, whatever's going on in the background to make this composition make sense. Let's just call this, let's say this composition makes sense. Okay. So now the question says, if each one of those maps is injective, show that this gigantic map is also injective. So I'm going to show you how this works with two maps. And then you can figure out how to do it with N. So suppose you have S1 and S2, and they're both injective. What does it mean for a map to be injective? What's the algebraic replacement for this? If I want to unwind this definition into an algebraic condition, what do I mean? Yeah. T of U is equal to T of V implies that U is equal to V. Okay, so let's suppose if we're trying to, so that means if I ever saw, if these are both injective, that means if I ever saw S2 of U is equal to S2 of V, I could write U is equal to V, right? And it also means if I ever saw S1 of U is equal to S1 of V, I could write U is equal to V, right? That would be the implication. So those maps being injective mean both of these conditions hold. So what we want to show is that S1, S2 of U is equal to S1, S2 of V implies that U is equal to V. That's what we want to show. I don't know this yet because I don't know anything about the map S1, S2, but this is what I'd like to show. Well, I don't really have any place to start. When you're doing an injectivity argument, you basically always start with the output statement. And we're going to try to do a bunch of algebra so this falls out the bottom. This is going to be the beginning. This is going to be the end. And our job is to fill in what comes in the middle. Right? So let's start with this. S1, S2U is equal to S1, S2V. Can I use either one of these expressions over here? Either this one, example number 1, this one, which I'll call number 2. Does either one of those apply to the statement I wrote down right there? But, well, yeah, right. Well, no, I don't think so, because, well, I mean, I guess we could do it that way, but it's actually probably more natural to think about it like this. A composition can be arranged like this, right? S1, S2 applied to U means do S2 to the vector U and then apply S1 to it. So S2U is a vector and S2V is a vector. So what does it mean if S1 of the vector of this vector is equal to S1 of a different vector? It must be equal. Why? Because injectivity gave us the condition, right? If I see S1 of a vector equals S1 of a different vector, those vectors must have been equal. That's what it means to be injective. Oh, so that just means I can yank the S1s off of the equation. So S2U is equal to S2V. Damn, I'm still not there. If only I had something I could say about S2 that would let me get to the last line of this argument. Well, look, I also know that S2 is injective, right? So, and that sure looks an awful lot like what I wrote right there. So that means U is equal to V. Now, all you got to do is figure out how to write that in a clean way with n maps composed with each other. But this basic idea is going to be the same. You're going to say, look, the outside map was injective. So that means whatever was inside of it must have been equal. And now the new outside map is injective. So what was ever inside of those must have been equal. And you just strip them off one at a time until you end up at the bottom where U is equal. Yep.
We want to have like algorithmic proofs that actually does.
If I welcome you to construct an algorithmic proof. I welcome you to do so. In fact, basically Axler's algorithmic proofs are just like fancy rewrites of finite induction.
Yeah.
Right. Yep.
So this one, like, in terms of that symbol.
Oh, okay. If you really want to, I mean, this would be an opportunity where you could. What's that? It does in this case, right? So the question is, okay, I don't know how many of you guys have seen this symbol before, but there's a symbol for, in the same way there's a symbol for finite sums, the big sigma, there's a symbol that stands for like a bunch of things multiplied together too. So the one thing you got to be careful about when you write something like this is you have to make sure that the reader understands that you mean that this is a non-commutative multiplication, right? And that you're multiplying from S1 to Sn, right? But yeah, I mean, what this means is in the same way that you use a sigma notation to record a sum, this means plug in the first thing, then multiply the second thing, then multiply the third, and keep doing that until you get to n. Yeah, I mean, this is a multiplication. You could use this symbol if you wanted to, because in the space of linear maps, multiplication is composition. So this was perfectly a big pi notation, we call it. Yep. The way this problem is set up, it absolutely is the case that n is finite. And so the setup here, you absolutely can do this with induction. And so, I mean, this sort of one step thing right here, you could very easily have replaced this with an n and an n minus 1 or something like that. Although you have to be careful because it means you need a symbol that stands for all of the previous stuff all multiplied together, which is actually one of these guys might be the most useful way to do that if you're doing the induction. Where there's a long-winded way with a lot of dots in it, right? I'll leave it to you to try to impress me with your elegance. I'm always impressed by elegance. Anyway, it's okay. I mean, the idea here is, I think, pretty straightforward, which is injectivity just cascades down. These things have unique inputs that they came from, then those must have had unique inputs that they came from. You just chain all the way down to the end. Anything else? All right. Okay, so what we're going to talk about today is, where's the chalk? So we're going to talk about matrices today. So finally, after all this time, matrices are going to sneak into the picture. So we're going to use fancy notation for matrix. We're in 3C now, which is entitled Matrices. So a matrix A, J, K. Now that might not look like a matrix, but I promise it is. This is what we're going to be defining. And the idea here is if M and N are positive integers, an M by N matrix, is a rectangular array elements of F. We're not doing matrices of matrices or anything. Whatever a matrix is going to be defined in terms of the field elements. Okay. That's written like this. A1, 1, A1, 2, out to A1, N, and 2, 1, down to A, M1, and then over here is A, M, N. M rows, N columns. Okay. So if I ever write AJK, what I mean is the entry A in the JK position, which also means the jth row in the kth column. The reason we use this notation is because it's obnoxious to write matrices down in sort of array form every time we write it. So, and I don't know if he does this, but the typical way of writing a whole matrix, instead of just like this, if I want to write a whole matrix, usually what I'll do is I'll surround it like this with parentheses, and I mean the entire array. And I could tell you J goes from 1 to N, and K goes from 1 to M. K goes from 1 to N. So this is another notation you might see for matrices. If I take this object, which is a single element, but then I surround it with parentheses, I mean, you are supposed to algorithmically reconstruct this array that represents. Yep.
How much does it matter to put the comma there? Can I just do A11?
Well, it depends on if I think I'm going to read it as A11. Right. Unfortunately, well, no, I mean, you say that, right? Like, you know, it's a reasonable question because matrices that show up in real life sometimes have like thousands or millions of entries in each row and each column. It's like the matrix that Google uses to describe the internet every time you go and search for something is like a 5 billion by 5 billion matrix. And it's a matrix. Oh, you guys have never seen how Google actually computes its search ranks?
They're not just a database.
No, man, you can't just do that. How are you going to get the ranking out the other side? So what Google does, actually, here's a brief aside into why this is cool. So like how these things are used in practice, what Google does is they look at the map of the entire way that the internet is linked to itself. So they record this huge database of links. And then they record it as a matrix that represents all those links. And then they use basic linear algebra actually to produce a vector that ranks the importance of every website that exists. So they take that 5 billion by 5 billion matrix and they raise it to like the 10th or 20th power or something like that. And then they apply it to, they multiply it by a vector over and over again. The vector you get out at the end is like the eigenvalue of the matrix actually sort what the most important matrices are, or the most important websites are. So yeah, Google basically, there's this really cool paper. This is an aside that you should read it. It's called the $5 billion eigenvalue. Eigenvector. Yeah, so if only you had been alive and had taken 206 in 1995, you could have used sophomore level linear algebra to make $1 billion. Yeah, I mean, this sort of like idea of working in matrices and translating things into matrices is like a huge practical idea. This isn't just a theoretical tool. Okay, so that's a matrix. So another definition. Matrix of a linear map. So this is one of the things that shows up in 206 and some professors teaching of 206. And it's one of the most important ideas in all of linear algebra, which is that linear maps have matrices that represent them. A linear map has a representing matrix that tells you what the linear map does. And the way you define it, like this. So, T is an element of the linear maps from V to W. And let's let V1 to Vn be a basis for V. And W1 to Wm. Okay, I'm just trying to make sure my subscripts matches. Basis for W. The way we're going to define a matrix, the entries of a matrix, is we're going to keep track of what T does to each basis element. This may be a fact that you remember from your 206 class, where you computed what a linear map did by looking at what it did to a basis. Essentially what we're recreating right now. So the matrix of T and I'm going to put a huge caveat in here right now. With respect to the basis, V1 to Vn and W1 to Wm. So the basis you choose for the vector space has something to say about what the matrix is. You choose a different basis, you're going to get a different matrix.
Sorry, is that the basis of V1 to Vn and the basis
Yeah.
of W?
Yeah. It's like this basis and this basis.
Oh.
So as
It's
soon
not
as,
combined.
yeah, as soon as you write a basis for V down and you write a basis for W down, you're basically fixing a coordinate system. That's essentially what's going on here. Like I could choose the standard coordinate vectors for R3 and my linear map will look like one thing. Or I could choose a rotation of that and the matrix will change. The map doesn't change, but the matrix has to change because the basis did. So changing the basis is going to change the vector or the matrix. So the matrix of T with respect to the basis V1 through Vn and W1 through Wn is an m by n matrix. With entries A, J, K defined by no TVK is equal to A1K W1 plus A2K W2 out to AMK WM. What the heck does that mean? What am I doing? This just looks like a pile of notation. How could this turn into a matrix? Okay, K is in the second slot here. Does K represent a row or a column? Like as I change my, so look, I've got these A1K, A2K, A3K. These are elements in some matrix, right? So let's write down a model of the matrix A to see exactly what the heck is going on here. So the first thing is, remember A11, A12, dot, 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 out to A1N, and then A21, A22, out to A2N, and then we go all the way down to AM1 and AMN. What number is changing when I do that? The first or second entry? Like as I go down this list of the A's, what's changing? The first entry. Does the first entry change in the rows or the columns of this matrix? Okay. So when I describe this list of coefficients, am I telling you a row of this matrix or a column of this matrix? I'm telling you a column. Which column am I telling you? The kth column. So the kth column of the matrix is the set of coefficients that come out from applying t to the kth input basis vector. Okay. I know this is probably a little confusing without an example. We'll do one in a second. But what's going on here is I take t and I apply it to the kth input basis. I look at what happens to that vector in terms of the output basis. And I write those coefficients down as a column of the matrix. That's the process to produce these things. If it looks nitpicky, it's because it can be. So what this formula is telling you is the kth column of the matrix T is the coefficients of a linear combination of VK. I know this is going to be better in terms of the WIs. How's that for a mouthful? The kth column of this matrix is the coefficients of the linear combinations of T of VK in terms of the output basis W1 through Wn. So let's write one down because that seems like really hopelessly vague. If you guys want. Yeah, so what's going on here is, so what are we actually doing? This is a good, very good question. So we've got some map T, right? Any vector I apply T to is in W, right? I mean, T of V is an element of W. But W has a basis, W1 through Wm. So every vector that's in W can be expanded as C1, W1 up to Cm, Wm. That's just true because this is a basis for the output space. So what does T do to any vector? T takes a vector in V, it spits it out into W, and then that can be expanded as a linear combination of that basis. So what we're saying is, if I picked the very special inputs where instead of just all V's, I just put in the basis for V and kept track of what happened, those numbers that came out turn into the columns of this matrix. Yeah, so let me actually, I'm going to do this real quick and you'll be able to see, hopefully you'll be able to see exactly what's happening here. So we're going to define a map. 41, cool, got lots of that. Okay, here's a map. Let's put T in the linear maps that take F2 into F3. And I'm going to give you the rule. T of xy is equal to x plus 3y, 2x plus 5y, 7x plus 9y. That's a perfectly well-defined map from R2 to R3, right? For F2 to F3. I want to find the matrix for T. Well, to get a matrix for T, I got to pick some basis vectors for my input space and my output space. What's the best basis you know of F2? That's pretty good. 1, 0, and 0, 1. Those are good basis vectors for F2. What's a good basis for F3? 1, 0, 0, 0, 1, 0, 0, 0, 1. I can't do anything unless I've got basis fixed before I start. So I fix a couple of bases. A basis for the input space, a basis for the output space. Does that make sense so far? Okay. How do I compute? What is V1? V1 is supposed to be the first basis vector for V. What should I use? 1, 0. What is T of V1? T of V1 is T of 1, 0, which is equal to what according to that map right there? 1, 2, 7. Well, now what do I do with it? That's not how I get the matrix. To get the matrix, I'm supposed to expand this as a linear combination of these guys, right? That's what it says to do. So how do I express this vector as a linear combination of these? Well, pretty easily. 1 times 1, 0, 0, plus 2 times 0, 1, 0, plus 7 times 0, 0, 1. That makes sense so far? I put in a basis vector. I got an output. I expanded my output in terms of the basis for the other space. What are the numbers that matter for the matrix? This number, that number. 1, 2, and 7. Are they a row or a column of the matrix for T? They got to be a column, right? 1, 2, 7 is column 1. Because when I put the first basis vector in, what came out was this particular combination. Now those numbers would be different if I used different basis vectors, right? If I chose a different basis, I wouldn't have 1, 2, and 7. I'd have different numbers. The map is the same, but the numbers would be different because the coefficients change with the basis. How about TV2? The TV2 is T of 0, 1, which is equal to 3, 5, 9. Where am I going to get some coefficients here? Oh, I'm going to expand it in terms of this basis I chose for the output space. 3 times 1, 0, 0, plus 5 times 0, 1, 0, plus 9 times 0, 0, 1. The 3, the 5, and the 9 were the coefficients of the output with respect to the output basis. So 3, 5, 9. That is the matrix that represents the map with respect to this basis and this one. If the basis had changed, the matrix would change. Make sense? So this is the matrix for T. With respect to the basis 1, 0, 0, 1 and 1, 0, 0, 0, 1, 0, 0, 0, 1. And if you have sort of ancestral memories of all that change of basis stuff that shows up in 206, all that change of basis stuff is trying to get away. Eventually what we're going to do is we're going to show that even if you pick a different matrix, there's a really easy way to change this matrix in response to that. The idea is T has a matrix that represents it, and we can compute it just by evaluating T on basis vectors. T has a matrix that represents it that we compute by evaluation on the basis. All right? This will come easier with practice, I promise. Okay. Now, I don't know if they told you this when you were doing calculus, but it turns out that calculus is also nothing but linear algebra in many ways. So let's pick a different map. Let's pick, I don't know, how about differentiation? And let's have differentiation acting from P3 of F into P2 of F. That's a reasonably well-defined operation, right? Third degree less polynomials when you take the derivatives turn out to be second degree or less polynomials. Maybe I want a matrix that represents this. What's the matrix for D? Differentiation is linear, so it should have a matrix. What do I need to get started if I'm going to write this matrix down? Okay, what's a good basis for P3? 1, Z, yeah, we use Z because it might be complex numbers, right? So Z, Z squared, Z cubed. There's our input basis. And our output basis is 1 Z, Z squared, right? Everything in P3 is in the span of these. Everything in P2 is in the span of these, okay? Let's do the same computation. How do I get the matrix that represents this map? Well, I apply D to each basis vector here and see what it does. D of 1 is, oh, well, that's not very interesting. So that's 0 times 1 and 0 times Z and 0 times z squared. Why did I do that? I have to write the output as a linear combination in the basis for the output space. These coefficients are going to turn out to be, so now let's record the matrix. So the column that corresponded to 1 turned into 3 zeros. Yep. What's the derivative of z? 1, which is 1 times 1 plus 0 times z plus 0 times z squared. Again, I need every coefficient because I have to express this vector in terms of this basis. The zeros need to be there so that I could write 1, 0, 0. How about d of z squared? 2z, which is 0 1s and 2 z's and 0 z squareds. 0, 2, 0. Okay. No ones, not 6, sorry. No ones, 2 z's, 0 z squares. And then finally, d of z to the third is 3z squared, which is 0 1s, 0 z's, and 3z squared, which gets you the column 0, 0, 3.
You're expressing like elements of the basis as linear combinations on the same basis.
Well, I mean, it's not the same basis here. It's a different basis because these are different spaces, right?
Where are you using the basis for P2?
That is when I do this expansion, right?
And why?
I put in vectors in P3. So I put in each element of the basis for P3, and I express the output in terms of the basis for P2. Okay. Okay, so what that means is, I mean, ultimately what we're going to be showing is that taking derivatives is just matrix multiplication. That's where this ultimately goes. Now, we haven't gotten there yet. We're just looking at the matrix that represents the function, but it's going to turn out to be the case that these get used to translate the action of linear maps into just matrix multiplication. All right. So how much further do I want to take this today? Got 10 minutes. Okay. Now, I don't have time to do what I really want to do right now, but I'm going to talk about it anyway, even if I can't actually do it. How many of you, if I asked you right now, could multiply 2 matrices? If I just wrote 2 matrices on the board and say multiply these matrices, be honest with me. Okay, iffy, right? Like, have you ever wondered now why can't you remember how to multiply matrices? Because it's hard and weird, right? The algorithm is really weird, right? How do you multiply matrices? So there's a whole thing where it's like, take this row and you dot it with this column, and whatever row and column you started with, that's where you put that's where the number goes in the array that came out. Have you ever wondered why matrix multiplication is set up that way? Those of you that know the answer, maybe you haven't, right? But if you ever raged at matrix multiplication, you might actually wonder why on earth would anybody ever set multiplication up this way? In fact, isn't there kind of an easier way to think about matrix multiplication? I mean, how do you add matrices? What do you need to know about matrices to add them? Well, they better be the same size, right? Because how do you add 2 matrices? If you have 1, 2, 3, 4, and you add it to 3, 4, 5, 6, what do? It's 1 plus 3, 2 plus 4, 3 plus 5, and 4 plus 6. So my question is, why don't we just define matrix multiplication the same way? Why on earth wouldn't this be the natural way of doing this? 1, 2, 3, 4 times 3, 4, 5, 6 is equal to 1 times 3, 2 times 4, 3 times 5, and 4 times 6. Why isn't this the way we did it? This just seems really obvious, right? It's the same exact multiplication that corresponds to the addition we use. I mean, it's obvious. In fact, this has a name. This is called the Chronicler product of matrices, or Schur product of matrices, right? So the Schur product of matrices says if they're the same size, you just glom the entries together. Wouldn't your life have been so much easier in your earlier classes if this is what matrix multiplication was? No crazy algorithm number, just are they the same size? Okay, multiply the entries. So why don't we do it this way?
Multiplying more sizes.
But why do I care about multiplying more sizes together? I can't add more sizes together.
Well, since composition.
That's an interesting idea. Okay. Anybody else have an idea? You've hit on something there. Shapiro said so. That's a, well, if we trust that Jonathan is the authority of all things matrices, which he kind of is, but.
Well, when you allow you to allow.
Yeah, but I can't do that when I add. Why would I need to? Who cares? So what? So I can't, I don't have like, it's not like I have a number and a 2 number comes around and I can take the 1 number and the 2 number and mash them together into something, right? So who cares? Yep.
If matrices are representations of linear maps, I think this probably breaks like what is it? What is it? What is the name? No.
When you're multiplying linear maps, it has to be like the rows of the first line equal to the columns of the second. You're treating the matrices like linear maps, and similar to composition, where the domain has to be
Okay. So that's at least 3 of you now have suggested that what's going on in the background is something to do with composition, right? That the composition of linear maps, this product that we defined, right? We have S and T where they make sense. The idea here is that matrix multiplication is set up not in this really nice way. Matrix multiplication is set up precisely so that if I take a composition of functions, the matrix of the composition is equal to the product of the matrices of the functions themselves. What I mean by that is, if S has matrix A, T has matrix B, S composed with T has a matrix. It's a linear map. It has a matrix, right? There's some matrix here. Every linear map has a matrix. Like C. What do you really want C to be equal to? I mean, if A is the matrix for S and B is the matrix for T, what would you really love C to be equal to? Not composition. The composition is right here. What map should represent the composition? Can't be T because T is a function. I want the remember, A is the matrix that we got by evaluating S on a basis. And B is the matrix we got by evaluating T on a basis. I can get this matrix by evaluating S composed with T. But if we're thinking about S composed with T as a product, what should be right here? What's the matrix for S? What's the matrix for T? Boy, would it be nice if the matrix of a composition was equal to the product of the matrices of the individual functions. There's no reason why this should be true. If I have S and T and I compose them, it doesn't have to be the case that something called AB is the matrix that represents the composition. So why do we set matrix multiplication up the way we do? It's precisely so that this is true. That if you have S represented by A and T represented by B, that the matrix that represents their composition is the product of the matrices. So that crazy definition of matrix multiplication is set up exactly so that this is true. Right? That we basically don't ever want to do this. We only want to be working with matrices. But to do that, I have to have some way to translate compositions down into matrices. And so that nutty definition, it's not so nutty when you actually look at what you're trying to do. You're trying to force it to be the case that this linear map has this matrix that represents it. And the matrix multiplication is the exact definition to make that work. So. And okay, and now why do matrices get to be multiplied at different sizes? Because there's no reason why the inputs and outputs of these things, I mean, the output of this matrix has to match the input of this one, or for the matrix, this operation to make sense, right? Whatever T is doing, it better be spitting out vectors that S knows what to do with. When matrices, that corresponds to the number of rows of one matrix and the number of columns of the other matching. The outputs and the inputs match. So that size thing where you guys write down m by n and n by r and the n's have to be equal in the middle, that exactly corresponds to when the composition makes sense. So mention matching of matrix multiplication is precisely the conditions when compositions make sense to compute. And rectangular matrices represent functions that don't map the same space into itself. If you have a 3-dimensional input and a 1-dimensional output, the matrix that represents it will not be square. Right? So there's this deep relationship between the matrices that represent functions and the functions that they represent. So the game of all sort of like this sort of linear algebra, this is the core of 206. Why spend all that time studying matrices? Because secretly you were studying linear maps the entire time without realizing it. All right, so I'm going to close this up because next time what we're going to do, I don't have time to do it. We're going to walk through why this is set up the way it is. We're actually going to formally write down what it means for this to be linear and show that it gives us the right definition of matrix multiplication. And then we're going to talk about, actually, where does he go with this? Yeah, so he's going to find matrix multiplication. And then we're basically going to head towards looking at why secretly all vector spaces are just Fn. Which that's kind of a letdown actually in the end, where it's like, oh, abstract vector spaces, but if they're finite dimensional, they're just secretly Fn, which is through isomorphism. Yeah. This is so what we're doing is we're building what we need to do isomorphisms in Fn. All right, see you guys next time.